Hi everyone. So in this tutorial I'm going to provide sort of a general overview into Dalton's law of partial pressures. Now essentially the main premise behind Dalton's law of partial pressures is that if I have a mixture of gases, each of these gas components are going to behave as if they're the only gas within the container that contains the mixture. So say for example I have a gas mixture with 3 components in it, okay? And let's assume, all right, that I wanted to calculate the pressure for each of these components. So according to the ideal gas law, the way that this would work is the pressure of the first component would be the number of moles of that first component times RT over V. Again, this is just a straight application of the ideal gas law. The pressure for the second component would be analogous. It would be the number of moles of the second component times R times T, once again, over V. For the third component, it would be, again, N3 RT over V. Now, it's important to note that if I have a mixture of gases, basically that mixture and all the components within the mixture would share the same temperature, so the temperature would be constant. And if we're talking about a mixture, then basically all of the components share the same volume. So the temperature and the volume are the same as each other. So that means I could, in theory, actually collect the RT over V terms as a constant and factor those out so that I could go and actually express each of these pressures as the number of moles times that constant that we get when we multiply R times T over V. So I'll just rewrite the pressure expressions, grouping those constant terms together. Okay, now where we're going with this eventually is if I have a mixture, then I might also want to get the total pressure of the mixture. Well, the total pressure of the mixture, PT, would be the sum of each of these individual partial pressures. So each of these pressures that are specific to the components, we refer to them as partial pressures. So I would have to sum all of the partial pressures, P1 plus P2 plus P3, to get the total pressure of the mixture. And so I'm going to actually go ahead and incorporate these terms that I derived before. So that would be N1 times RT over V plus N2 times RT over V plus N3 times RT over V. Okay? Now notice, if I go and think back to my rules of algebra, this is a common constant term between all of the terms of the sum, so I could go and I could factor that out. So I could also express this as N1 plus N2 plus N3 times RT over V, and I can also define the sum of the number of moles of the component as the total number of moles of the component times RT over V would give me the total pressure of the mixture. Okay, well, suppose that I want to take a ratio over the pressure of one of the components against the total pressure of the mixture. So suppose I want to get a ratio between the pressure of the first component divided by the total pressure of the mixture. If I go ahead and substitute in the expression for the partial pressure of the first component and the total pressure of the mixture, then I would get the following. I would get N1 times RT over V divided by NT, the total number of moles, times RT over V. Again, since the RT over V terms are constants and they're the same as each other because we're working with a mixture, then basically that ratio of constants would equal 1. So that means that the ratio of the partial pressure of the first component divided by the total pressure is actually equal to the ratio of the number of moles of the first component divided by the total number of moles of the mixture. This ratio, N1 over Nt, we can actually refer to that as the mole fraction of component 1. And mole fractions have the following symbol. It's actually the Greek letter chi. It looks sort of like a squiggly X. But in any case, basically this would be the mole fraction for the first component. Now, as it turns out, that's important because if I substitute that into this equation that I've derived, that means that the partial pressure of the first component divided by the total pressure of the mixture, that's equal to the mole fraction of the first component. If I rearrange so that I isolate the partial pressure of the first component, that means that the partial pressure of the first component is equal to the mole fraction of the first component times the total pressure. So this allows us to actually calculate the partial pressure of a component as long as I have enough data to calculate the mole fraction of the component and if I'm also given the total pressure of the mixture. So now that we've derived the important relationships that are involved with Dalton's law of partial pressures, let's actually practice applying them. So here's an example problem. Suppose I have a mixture and it contains carbon dioxide, nitrogen, and oxygen. And the mixture actually exerts a total pressure of 760 torr. The partial pressure of carbon dioxide is 0.285 torr. The partial pressure of nitrogen is 593.525 torr. They want the partial pressure of oxygen. Well, according to Dalton's law of partial pressures, for this mixture, the total pressure of the mixture should be the partial pressure of carbon dioxide plus the partial pressure of the nitrogen plus the partial pressure of the oxygen. If I rearrange, solving for the partial pressure of the oxygen, that's the total pressure minus the partial pressure of the carbon dioxide minus the partial pressure of the nitrogen. Substituting into this equation, I would get 760 torr minus 0.285 torr minus 593.525 torr. Okay, and if I actually do this math, then basically I get 166.19 torr, and if I round, then I get 166 torr. Okay, so that would be how I would calculate the partial pressure of oxygen in this case, and this is just simply an application of Dalton's law of partial pressures where I simply have all the pressures of the components but one provided to me. But this is actually a rather simplistic example of Dalton's law of partial pressures. They do get more complicated than this. For example, suppose I'm told that I have a mixture of 2 moles of hydrogen, 3 moles of ammonia, 4 moles of carbon dioxide, and 5 moles of nitrogen. And this mixture exerts a total pressure, so this is my PT, of 800 torr. What is the partial pressure of each gas? Now, you could, in theory, suppose if I wanted to calculate the partial pressure of the hydrogen, I could take the number of moles of the hydrogen, multiply by the ideal gas constant, multiply by the temperature, if I had it, and divide by the volume. But notice in this case, I'm missing the temperature. I'm also missing the volume, so I can't use that approach in this particular problem because those two pieces of data are missing. But if you recall, based on our derivation, I could use this equation right here. Okay, I could, if I find the mole fraction for each component and multiply that times the total pressure, then I could actually calculate each of these partial pressures. And so if I add up the moles of hydrogen, moles of ammonia, moles of carbon dioxide, and moles of nitrogen, basically that means that my total number of moles is 14 moles. Okay, that's important because if I want the partial pressure of hydrogen, I would need the mole fraction of hydrogen, so number of moles of hydrogen, over the total moles times the total pressure. So for the hydrogen, that would be 2 moles of hydrogen, 14 total moles over all the components, times the total pressure, which was 800 torr. Okay, if I do that math, then I get 114 torr. Okay, if I follow a similar approach, I could do the same for the ammonia. It would be the number of moles of ammonia divided by the total number of moles over all of the components in the mixture times the total pressure. If I plug in the numbers that I've got, that's 3 moles of ammonia over 14 total moles times the total pressure of the mixture, which is 800 torr. That would give me 171 torr. And so I would follow the same procedure using the corresponding number of moles of each component that are left, following the same exact calculation that I've shown for the first 2 components. And if I do that, then I get the following partial pressures for each of the components. I'll leave it to you to verify yourself, but you should get the following pressures for each of the components. Okay. One last example that I will go and demonstrate for you is what happens when we try and actually apply Dalton's law of partial pressures to a practical situation. A lot of times when we're studying a gas, especially a gas that's produced in a chemical reaction, it's common practice sometimes to collect that gas over water. So when we collect the gas over water, essentially what happens is we have a gas being evolved in this test tube. And essentially, as the gas is produced, it travels through this tubing and ultimately travels through the water and gets collected up here in this particular vessel. Now, in the vessel, we have the gas of interest, but we also have water vapor that we have to account for. And so this is an ideal application of Dalton's law of partial pressures. Because, for example, suppose that I collect a sample of gas over water at a temperature of 35 degrees Celsius. When the barometric pressure, right, which is the pressure of the atmosphere, is 742 millimeters of mercury. What's the partial pressure of the dry gas? Well, I have a mixture in this particular vessel that's composed of the gas and the water vapor. And so that would mean that the total pressure of this mixture is the pressure of the gas plus the pressure of the water vapor. Now, the pressure of the gas is actually approximated by the pressure of the atmosphere. And this is done by actually manipulating the experimental conditions so that the level of the water within the container is allowed to be equal to the level of water in the basin that holds the water underneath the apparatus. We'll discuss this more in class tomorrow. And so I can use the atmospheric pressure as an approximation of the total pressure of the gas mixture, which comprises the gas of interest and the water vapor. Now, water vapor has specific pressures at specific temperatures. So I would need to go and look up this vapor pressure of water, and that vapor pressure changes with temperature. So I'd need to look it up at 35 degrees Celsius. And so it can be provided to you in a problem. You might be given a table, or if you have access to the internet, then you might be able to do an internet search. So for example, I'm going to go to Google and search for the vapor pressure of water at 35 degrees Celsius. Okay. And if you take a look, basically you'll see that the vapor pressure of water at 35 degrees Celsius is 42.2 torr. So I'm going to go ahead and incorporate that in my calculation. This is actually 42.2 torr. So I'm going to solve for the pressure of the gas. The pressure of the gas is then going to be the atmospheric pressure minus the pressure of the water vapor that I just found. Substituting in, that's going to be 742 millimeters of mercury. If you'll recall, torrs and millimeters of mercury are the same unit, so that would be minus 42.2 millimeters of mercury, and that's going to give me 699.8 millimeters of mercury for the pressure of the gas of interest. So go ahead and work on the follow-up assignment as best you can. We will discuss this topic further in class tomorrow. Again, if there are any questions, email or ask questions in class tomorrow. I will see you guys tomorrow.